Oh, okay. Should I give them like a quick one-line introduction for you? Oh yeah, Vin cannot. He has no mic. All right, so Vin, he is lead data science of Trusting Social. He's one of the mentors on the network, and extremely friendly and helpful guy, full of knowledge. So yeah, definitely should reach out to him if you guys are interested. Dev, is your mic working? Maybe you want to do an introduction.
Hi, can you guys hear me clearly?
Yeah, can hear you.
Okay. So you can call me Dev. I'm basically a community manager at Hasbrain. I'm take care of those kind of meetup and running event and workshop, reaching out to the mentors or the industry practitioners network to connect enthusiasts with practitioners. So basically, those activities to help to connect the community and everyone can learn learn and exchange thoughts from each other. So if you wanna connect or if you need any support from me, feel free to reach out to me at the email I left on the screen at hasbrain.com, or feel free to join the Slack and Facebook group channel. I'm pretty active and will be very responsive if you need any help.
We have some faces like Duke. Vin really introduced.
I think Duke has joined one of our demo class, deep learning, the practical
Cool.
class. Maybe Duke, do you want to give a quick introduction?
Maybe they are like waiting for the discussion to start. Oh yeah, cool. Yeah, I can hear you.
So hi everyone. I'm Duke and I'm new to Hasbrain. I just joined this community, and so right now I'm working for a company that work in IoT, and they are they are researching about AI in computer vision, and I'm working for the computer vision system. And yeah, so I'm kind of like research about AI in application for IoT. So nice to meet you.
Nice to meet you. Which company is that? I think is that a camera company that does like detection?
Maybe it's not familiar with you guys, but its name is Smart Tech, and it is a startup and a branch of a French company, and French company is Elec. So yeah.
Cool. Ultra cool. Welcome.
Yeah.
Fook, do you want to go next? I actually don't know whether they're online. Or Fook or like maybe Fat. Oh, no problem. Maybe you just type. If you can't talk, just drop like a 1-2 liner about yourself. Okay, okay, maybe who else? Just do Quinn, do you wanna a note about yourself? Okay. I don't know whether you guys can hear clearly or like I think a lot of the mics are not working. But in any case, I'm actually gonna start now since like I think I think most of the people are gonna be here or here.
So you guys hear me now?
Great.
Okay.
Your
So
mic is working. Awesome.
yes, the problem is I mute myself.
Oh yeah. Okay.
Yeah. Sorry.
No problem. Let me figure out how to share. Okay. Dev, I need to share screen, so you need to like stop sharing screen.
Yeah.
Daphne, you need to stop sharing. Yeah. Okay, cool. Okay, let me do the keynote. 3. Oh, sorry, something wrong. It's screen 3. Oh, let me figure out the screen sharing part. That's it. Where is the keynote? Sorry, one sec. Keynote. It's out. Okay, awesome. Right. Okay, guys. I guess some of you know me. I'm gonna do a quick introduction of myself. I think even for those people who know me, probably don't know this part about me. I started like machine learning actually 14 years ago, and I was building a Bayesian particle filter for localization, essentially collecting Wi-Fi and Bluetooth beacon like strength and trying to do localization within like a small space. And then like in 2016, we started nonprofit classes working with local experts. During that time, we also started a marketing analytics company to help do prediction and user collection and content interaction for media companies like Fox, DreamWorks, a bunch of Taiwanese media broadcast companies. And like now we are mainly focused on helping to understand how to train human intelligence using AI. And we're very interested in the question of how do we apply that to massively scale the best knowledge in the best way delivered to the masses, especially those who traditionally do not have access to this knowledge. So I'm currently also an instructor at the Google AI Bootcamp. So why do we organize this? Actually, there has been some good, I have benefited from some of these paper discussions and meetups when I was in Silicon Valley last year. So I wanted to actually start something in Asia too, because I don't find anything that is consistently doing this. And this is not like only experts that can come up and present. I think we learn many things during our daily interactions from work or from other people, or for things that we hear about. And this acts as a safe space. If you have something that you read about and you're interested to present and share and discuss, this is where we want to do it together, right, on a weekly basis. It doesn't need to be you know everything. I think it's just something you found that's interesting. And even if you don't know everything and someone asks a question, it is fine, because like there are other people who might know something, or we can just research on it together. Okay. And so to sum up, it's really just a space where everyone can be together consistently and work on new knowledge and share knowledge, because I think that's the best way to improve, right? Like as with every training, or if you think of the human mind as a deep learning, like extremely complex neural net, then definitely with more data, more interactions, we're gonna get better. Yeah, so that's the whole idea. And there doesn't need to be perfect training examples. It just needs to have more training examples. Okay, so this is not really a presentation. This is more of a discussion. But I know that, you know, so like you guys just chill. It's Saturday morning. Anyway, really thanks like for highly appreciate everyone who is here. I think we are starting from, this is our first session, starting from a small group. So just feel free, this is like almost like a chat among friends, okay? So feel free to just stop me and ask questions when you have any. Cool. So today we're actually discussing, sorry? Oh, hi Ahmad.
Hello.
Welcome.
How are you? Thank you.
So I was doing a high level introduction of myself. You can, yeah, so welcome to the group, and we're sharing about the community like guidelines. So this is not really about only experts presenting. I think it's about us like whatever we have learned on a daily basis to come and share knowledge together. So I'm an instructor at the Google AI Bootcamp and started some AI analytics company previously, and is also currently working on one now. Okay, going back. So rethinking ImageNet for pre-training. I'm excited about this paper primarily for a few reasons. This is something that is very basic. It's like just using pre-training data. I think it's almost commonplace now. But I think this paper presents a interesting view on what actually happens when you use like pre-training data, and also like what are the limitations. A lot of times when we train things, we just go like, okay, this is not working, not enough data. But I think there are several things that are pretty basic that is highlighted in this paper that we can consider. And I think most of the time, like for us, we don't actually have the time to go and break it down and do experiments on those things, especially for those of us who are not in the research area. For the production environment, I think we are mostly focused on delivering results. So almost all the time, I think pre-training is better, right? But is that true? So this is what we're going to discuss today. So is pre-training better That's the first question. Or rather, it's better, but is it always necessary? And for what task? And this, I'm actually, the reason why I chanced upon this paper is actually I was researching on object segmentation and character. We're just building like a. I was doing this as part of my hobby apps. Just building an app where you can take a picture of any slides. Because I always go to meetups, and then there are sometimes you want to take notes on the slides too. Like I just take a picture of it, and I kind of want it to automatically save the notes in a readable fashion. So I was just like hacking out some stuff, and I chanced upon this. I also heard of it from another meetup that I went. And so the question is always like, if you're trying to train something, like whether pre-training data is necessary, and how much or how little data is like needed before it becomes necessary. And are there any special techniques? So I'm gonna give you, we're gonna start with the end in mind, which is essentially the paper shows that with enough data, and we're gonna define what does enough data mean. It's actually not necessary. You can actually get slightly better results if you're not just working on classification, right? So for more complex tasks like object detection that requires some spatial intelligence, so it's a slightly different task, and training it from scratch might be slightly better. And then the question is, if you are doing a production system, does the slightly better warrant a 3x more iteration cycle? Maybe not, but maybe for those of you who runs Kaggle competition, this might be something interesting. And it actually works for like deeper and wider models, and there are different ways to basically make sure it works for those. The techniques to treat them are different. Yeah, so this is the conclusion of the result. So for those of you who are like, oh, okay, like you want to know the high level 3 minutes, this is basically it. The rest of the discussion is mainly on the details, right? Like how it is done. Hopefully most of you have somewhat skimmed through the paper, or for those of you who have read it, feel free to drop in additional insights you have. These are all, like, a lot of it is based on what my own takebacks from the paper are, like what I feel like are the good learning points. But I don't actually want to cover everything in depth, because that's almost like reading the paper back to you. But for those of you who have like alternate views on this, feel free to drop in notes as I talk. All right, so past work done. This, I think, like the actual object detection, the original model is actually based on pre-training data, ImageNet. And there's always an implicit assumption that if you want to do that, the only way to do it properly is to use pre-training data. And then there are works that people have recommended. Oh, like with normal architecture, you can't actually do it. You can't actually train from scratch for object detection. You need special architectures, and there are a few proposed. So this paper is interesting in the fact that it tries to use like the typical algorithm that's already being used for the Coco competition previously, and it tries to prove that even without pre-training data, we can actually get there, which is not intuitive from my prior knowledge before reading this paper. Because like, I guess we never actually went that far to train that many iterations. It kind of like, typically when it starts to converge, then we stop there as a result that we'll take. At least that's my behavior. Not sure about the rest here. So there are a few things that needs to be done before the experiment can be set. The paper talks about actually like a few key items that you need to take note, because there are prior experiments ran that says basically if you train from scratch, you'll never get good results or comparable results. So the paper talks about limitations in some of this, or common mistakes that are made in some of these papers, or like so normalization of the data is not properly done, and it goes a bit to talk about the idea of for if you are training a deeper network like ResNet, you will need to take note of the activation normalization. And typically, if let's say you are training this on your desktop computers, like maybe 4 or 8 GPUs, they don't. If you understand a bit about how the memory is being passed for batch normalization, it requires it to be seen like if the batches are too small, actually a lot of the advantage of batch normalization no longer takes place. So you need to apply like alternate normalizations for those cases. So there is basically group normalization and synchronized batch normalization. Synchronized batch normalization, to think about it, is quite simple. It kind of treats like all your GPUs as like a single unit. So it increases like it trains it as the same like unit. So it can it's almost like equivalent of you having like a bigger memory like GPU, right? So you get a bigger batch. Or the alternate is to use like group normalization. So that's the first one, is actually normalize the activation. And then the second point is quite interesting for me, is how much data is actually enough, and how do we define data? Because for object detection, there are a few things in place, right? It's not like classification. Classification is like, I give you an image, then you tell me it's a cat or a dog. So basically it's the total amount of images, and then the resolution of each image doesn't really matter as much, since it's really just, as long as you can kind of see the object within the image, I think that's kind of fine. But for object detection, you're trying to detect like objects within the image, so resolution matters. And then instances, for those of you who don't really do object detection, instances means like the number of objects within each image. So like for Cocoa dataset, I think there's around 7 or 8 instances for each image. And then for classification, you can kind of think of it as one instance in each image. So this graph basically shows the amount of data. So I think how the experiment is set up is such that if you use pre-training data, they put it as part of it. So Cocoa is much higher resolution compared to ImageNet. So ImageNet has a lot more pictures. So if you look at the graph, basically ImageNet is the gray. Let me see if I can do a pointer. Oh. Okay, I don't know. I don't really think you can see the pointer. Sorry, one sec. Pointer. Annotate. That's fine. I can't figure out the pointer. That's fine. All right. The gray part is basically all the part for the ImageNet. I think you guys can read. Like the pink is the Cocoa for random initialization. So the idea here is that if we are just doing fine tuning, right? That's like they are doing 24 epoch. And for the random initialization, they triple it. So basically all the pink regions are 3 times of the green regions, because they just, this graph is to show you how much data actually passes through the algorithm, right? So if you run like 3 times more epoch, you basically have 3 times more data. That's the way to think about it. It kind of took me 3 minutes to understand what they're trying to say, but yeah, so I'm just breaking it down for you so that you don't need to waste that 3 minutes. So any additional questions or input about this chart? I think it's pretty straightforward. So it's kind of to show you, like, in terms of pixels, if you look at it, it's comparable, even though you're not using ImageNet as a pre-trained data set, but because Cocoa itself is, like, the resolution is big, so you kind of get comparable data after that. And this is interesting to me because it's not, I never thought of it as resolution level. I always think of it as, like, images. And there is an experiment now going on that they are trying to train, like, a universal pre-trained data set. I'm not sure if you guys are aware of this, because, like, so they have huge successes for ImageNet, right? But the images are still kind of low res. And then the idea here is that, okay, what if we just pre-train, like, classifications on, like, a way bigger, like, resolution? Like, I don't know how much time, I think it's like 10x bigger or something in terms of resolution. And then will that yield better results? And it kind of points to a general direction that it does for similar tasks. Like, if you're doing classification, it does yield better results. But for, like, object detection, it doesn't really. So this slide is basically just to give you the question of what is, like, amount of data and how much is needed. And I think this is a great precursor, because a lot of times when we start off an experiment, I think, at least for me, I don't know about the rest, maybe you guys can chip in. The first thing I will do is actually go look for data. Like, when I'm doing, like, in the toy experiment that I'm doing now, which is taking a picture of any, like, slides, and then it actually saves the text. I mean, the first thing I did was to go and Google for data sets, right? And the data sets are all in different formats, obviously. And I need to spend time to clean up and then merge it. So the question of how much is enough is kind of interesting for me. And actually, all the data sets that I found have varying, like, resolutions. And then how to treat them in a way to make it consistent. Like, should I drop, like, the lower resolution, like, data sets, and then just go with the higher ones, and then how much is enough? So this gives me an intuition of how to approach that. Basically, like, higher res will be interesting if the task is similar, and object detection typically takes higher resolution. And in general, actually, the accuracy for object detection is not high in itself. But anyway, let's go on to back to the paper. So these are the results. And so after you normalize it properly, you can see that basically the final results are comparable, right? The only thing that needs to happen is more iterations, like a lot more iterations, like 6 times more iterations. So if you have money in terms of GPU, or you're just running your own GPU at home, and you're actually trying to win some Kaggle competition, it actually might be a good idea just to train from scratch. But if you actually look at the chart, I think what's interesting is the pre-trained models are slightly lower than the random init models. Like, for the cascade, you can see with augmentation, it's around, like, 48.6 versus 48.3. And in the production environment, I guess it really doesn't matter. It's a cost versus value question, and that little increment probably doesn't warrant you to train everything again. So what is likely going to take place in the production environment is still to use pre-trained data. But again, for Kaggle competitions, maybe this is worth the time. And then for those of you who don't really do object detection, this paper talks about using Cascade RCNN, which is quite common, and it gives you better results. Yeah. Okay, so yeah, this is the chart to talk about, like, basically how much more iterations is needed. At higher number of iterations, it actually converges to to be similar results. So like if you're just doing like, I think 2x is 180 iterations, 180K, it doesn't actually, it shows that the pre-trained model is still better. But as you go higher, I think it basically just tends to the same. Okay, and this is more interesting for the object detection part. The previous measure is, this is a better measure for object detection. BB box is, okay, I tried to find like images that makes it more explainable. So on the left image is basically on like, if you talk about object detection, you talk about what's the ground truth versus what is your predicted box, right? And how much it overlaps. And then BB box 50 is it just means like 50% and above overlap. 75 means 75% and above overlap. And actually what you can see from the results is that for object detection tasks, for pre-trained models, the results accuracy is actually lower. And then the right-hand side of the table, which talks about is more on segmentation rather than just the bounding box. So as the task actually deviates more, I think the pre-trained model becomes weaker. I think that's the intuition. So they also changed like the model that is used to train. Instead of using ResNet as the backbone, they switched it to VGG. And the results are similar. The only intuition here to gain is that for VGG 16, it's harder to converge. And then the treatment, because VGG is a more shallow net, you don't actually need to do like the batch normalization, but you need to do the init normalization. Okay, so for me, I think this is a really small point in the paper, but it kind of is my own take home. Like I put it down in my own notes that, you know, like it's not always valid to just take what is the recommended hyperparameters based on previous competitions. It's always a good idea just to perform grid search again. I think there is a small point about this in the paper, and this is like I think this is one of the take-home points for me. It just doesn't take much more effort, so just run it again to get better hyperparameters. And also the other point that they were making is that like pre-training doesn't help you guarantee that there is no overfitting. Just because there's more data, it doesn't actually mean that there's no overfitting. Which is again counterintuitive for me, because I think the foundations is always teaching you that more data can help like combat overfitting. So, but as you actually, the question is, it may help like in the case where you're using like hundreds of thousands, but then as the primary training data set goes down to lesser data, you need to take note of like the other foundation pieces, which is like the hyperparameter tuning. Okay, cool. This chart is quite self-explanatory. The only thing to note is actually this is 5 charts in one, and so they ran it at different. They ran it with different number of iterations in mind. So the first, you see like there are 5 peaks here. It's because like at each end of the peak they reduce the learning rate by 10 times for the last 60 and 20K iterations. So every time you reduce the learning rates, it basically jumps up in terms of the accuracy. I don't think I'll go deep into that. I think it's pretty intuitive. Basically, you're just trying to hone down to the point that you want to kind of just finish off your training. But I think the takeaway from this chart is basically the difference between the number of training images. So less training images, you get less accuracy. Sorry, does someone has a question or a point to make?
Hello.
Hey, Ahmad.
Yeah, I actually have a question here. Do we have like separate question session after this, or do you keep on going and we ask later, basically?
Oh, yeah, this is mainly a discussion. Like, you feel free to stop me anytime if you have questions or additional points, but we will have one at the end too.
Okay.
So either
All
is
right.
fine.
I'll wait then. I'll wait then. Keep going.
Cool. Yeah. Yeah. So intuitively, again, I think the results still speak for itself. Like at lower iterations, you can see the pre-trained model is higher, and then at the but as you go on higher iterations, they kind of converges up. So this is kind of my final slide. So these are actually the learning points for me, and there are different takeaways for different people. So I'm just gonna say mine. Basically, don't be lazy. Do research. Just to do the hyperparameter tuning again. And then for activation, so for deeper models like using group normalization and sync batch normalization are good ideas when you don't have like huge ass GPUs that are specialized. But from the results itself, I see that GN is actually better. And generally, transfer learning and pre-trained models is still useful. I think even especially so for production level systems where you don't actually care about the last like 2%. And then the other take home for me is it changed the way I think about amount of data in the sense that it's images and actually instances and pixels that matter. Because there's this other point made in the paper that talks about, I think they did the training not on the Cocoa dataset, but it was the other dataset. It was Pascal Vox or something. And the number of instances is way lower. I think it's 3 times lower. And they realized that even at 15K images, it didn't have the same results. It's almost like the training from scratch doesn't have enough data at that point, just because there are not enough instances. Yeah, and so this is like kind of the end. So if anyone has questions, this is the time to drop. Ahmad, do you want to?
Yes,
Yeah.
perfect. Can you please go back one slide? Yes, that one. So in the left-hand side, the 35Ks, do we have an overfitting issues with the pre-trained data set?
Right. So the question is basically at 35K whether we have a overfitting issue. I actually don't think there is a overfitting issue. I mean, like, where do you have like a context as to why
35?
Yeah.
On the 35, after 1.5 iteration, it seems as like it's a small, like these spikes that goes up all the way, and they seem to converge eventually. Are these considered overfitting problem?
Oh, so yeah, so there are basically 5 experiments that's being ran on this chart. You're aware of that? Is that correct? So there are like I think they ran it from like, it's like 15,000 I think iterations, and then it's like 25 and then 35 and then it goes all the way up.
Mm-hmm. Yeah.
So your question is for the lower iterations, is that correct?
Yes.
Whether it's overfitting issue. I don't think there is, because they actually, I think if you have done the in the experiments, they actually did the grid search for the hyperparameter tuning, and then it's actually noted that if you don't do that, then you get overfitting. But then after that, it's actually noted that there isn't any. But I would like to hear maybe from the ground. Maybe Vin, do you have comments about that? Vin, are you there?
Yeah, you hear me, right?
Yeah. So Ahmad has a question about like whether from the graph there is overfitting. I don't actually think so. I think maybe Ahmad, do you want to like explain a bit more about which part of the graph you think that
all right, so I think maybe 1300 or like 1.3 iteration after the first cycle. There's a 36.1.
Yeah.
I know. Is this considered overfitting?
Vin, what do you think?
Anyway, how can we see that? I mean, how can we see that with just one graph? Is the point?
Yeah. Yeah.
All right, so it's probably not enough to judge or like.
Yeah, I think overfitting is when you need to take a look at the test data and the validation data.
Correct.
Yeah. But the paper actually talks about like there is no overfitting. But you need to do the you cannot tell from this graph conclusively, but you need to do the actual tuning for the hyperparameters.
All right. Okay.
Yeah, but it's just, I think the interesting point is the kind of sum up or breakthrough at the certain level. Yeah, never see that before. Yeah.
I think it's because of the optimizers they use. Like they did like a custom one where in the last 70, I think last 60 or 70K and the last 20K iterations, they reduced the learning rate by 10. So it kind of just like, like the loss basically goes like, it basically iterates much faster to the endpoint.
I see.
Yeah, I see. Yeah.
Yeah. So I think that is because they did a custom optimizer. And the breakpoint is basically 3.5K to 10K images. So like, if you think about it, it's basically 10K, and Coco has like 6 instances each. It's like 60,000 instances before it. So once you have 60,000 instances, it kind of doesn't matter anymore. And 60,000 instances with enough resolution. Yeah. Yeah, so cool. So this is, yeah.
I want to say that this paper is pretty essential, but I find it very intriguing because it's it's shedding some light whether to use the pre-trained data or not. Sometimes the initialized, the randomly initialized, can be better, and like you said, they don't automatically. The pre-trained data does not automatically reduce the data, the overfitting.
Yeah, and I think I mean, I have seen myself doing it last time where like I automatically conclude that, it's not enough data, right? That seems to be like the only thing that people think about, but they don't actually also think about, okay, what are the other points that I've missed out in terms of, the hyperparameter tuning, have I done like normalization correctly, stuff like that. And I think these are just reminders to like fundamentals that are important. Cool. Does anyone else have additional points? No? Okay, I'll spend like the last few minutes to talk about like other stuff that I'm working on, but it's a bit more advanced. So I chanced upon this talk, this Stanford talk, where it is trying to talk about, I'm not sure if you guys heard of this, like basically you're trying to tell the AI, like, so you have an image, so imagine like an image of a picture of like maybe of a park, right? And you want to ask the AI some questions like, tell me what is on the right side of the tree behind the man. And then the AI is supposed to reply you, oh, it's like a boy, like it's like a boy in a red shirt, something like that, right? And the talk basically is for the pursuit of general intelligence, how, like, what are the thinking behind it. So they talked about this thing called the attention perceptron. Not sure if any one of you guys have read that paper. It's out recently. But yeah, I think that is quite interesting. Might be a bit deep for the paper discussion at this point, but I think it'll be very interesting if anyone in the group now has other papers to share in the following weeks. It can be something simple. I don't think it needs to be highly complex or cutting edge. I think for me, my take-home point is like basically I've spent an hour plus to read this paper. I think it's like a way more fun way to actually get a download of papers. There's just so many papers out there, and like I'm sure you guys read papers as part of your work, or like if you don't, then just turn up for the meeting and then listen to other people talk about it. It's just like a more compressed version of it, and then we can take on like intuitions. So if any one of you actually have papers to talk about in the future, I think that would be cool.
I have a small question as well regarding the. So you said that in classification models, we don't actually have to consider like the pixels. Like it can be lower pixel, and it can function and work correctly. But in this paper, it seems to actually matter if we have bigger number of pixels. So how does it actually work? Like, could you explain that?
Right. I think actually, to me, it sounds like from my takeaway from the paper is that, I mean, the first part, the author talks about pixels. Wait, there's this graph there. So pixels actually matter, right? But I feel like from my take home from the results is that instances matter more, if not, like I think instances itself matter more. But once you cross like the baseline instances, then having like enough pixels matter at that point. So I think it's like intuitively for me, it's a two-step approach, because if what they're saying is that pixels is the only thing that matter, then the other data set would have worked as well, but it didn't, right? Just because there are way less instances. So instances is actually the first, like just having enough data about like examples itself is important. And then if you have enough examples, then you looked at whether the examples are high resolution enough. Because when you do object detection, it's a subset of the image. It's not the whole image. Does that make sense?
It does. It does. Thank you. Yeah.
Yeah. Cool. Okay. Yeah, I'm actually gonna build a open source example about the digit segmentation from images. So I will share it to the group when I'm done with it. And actually, it forms part of the Google AI Bootcamp that I'll be giving next week. So if you guys are interested to check it out, let me know.
Yeah, cool.
Yeah, Vin, yeah, we'll love to have you there too.
Yeah, so basically, just want to share with you. I think I discussed briefly with Daph. Hey, Daph, you there? Hello.
She's kind of there.
Yes.
So yes, I think it's a really good idea to, continue this kind of series. Either me or I will try to coordinate more speaker. Okay, you hear me?
Yeah.
I will try to coordinate more speaker into this kind of series. My personal idea on my personal opinion in this kind of series, we just focus on one or two paper and really go deep. Rather than a topic. That not really a general topic or not really a topic, but the topic is a paper. So it's really kind of reading just one or up to two papers.
Yeah.
Yes, either I will do that, or I will coordinate speaker mostly in Ho Chi Minh City around here. But I will see if I can find someone else I mean, outside,
Cool.
and
Yeah.
I will let you know on that.
Yeah, I think we have interest from Singapore. And Ahmad, where are you from?
I'm from Egypt, actually.
Oh, cool, cool. Like, yeah. So I think there are interest from all like people all over the world. I think from our side, I think I have like ideas of like a lot of people in Singapore who will be interested in this too. And then to your point, I think you're right. Like if the papers are like deeper, like I mean this paper I could kind of like sum it up in 30 minutes, right, with a few slides. But I think some papers are very deep in math and they might take like 1 or 2 sessions. And then for me, it's basically like just getting an idea of how to apply this going forward. I think that would be very interesting too. So for me, I think the next part in this is I will try to share some code that I have for the community and see like whether we can learn something from it. Yeah. Okay. Well, guys, thanks for joining us this Saturday. And Ahmad, thanks for joining us all the way from Egypt. Like, appreciate your time here.
Thank you very much.
Yeah. We will continue this next week, and like Vin, maybe I'll talk to you about what papers might be interesting. And then we can take it up from
sorry,
there.
I mute myself again. Okay.
Okay. Yeah. All right, cool. Guys, have a good weekend. We'll catch up soon again.
Yeah, bon weekend. Bye bye.
Bye-bye.
Bye bye.
Bye.